Hello, this is Yukio Watanabe at Mechanical Simulation Corporations. Advanced driver assistance, active safety, and collision avoidance systems are not available yet with current production motorcycles. However, in order to provide the cutting-edge simulation tools, BikeSim shares the most of ADAS features with the sister product Cashman TruckSim. So, I would like to demonstrate those features.
This animation shows three-lane traffic involving one motorcycle, which is full vehicle dynamics model, and other cars that's a moving object. The motion and appearance of objects are set on the multiple moving object screen. This is a middle lane traffic involving two cars whose speed is specified as the same as the on motorcycle speed. The right lane is 3.5 meter right from the center lane, and there are 6 cars running with 95% of their own motorcycle speed. This means a little slower. And the left lane is 3.5 meter left from the center lane, and there are 6 cars running with 110% of their own motorcycle speed. Another example, we are looking at the extending the behavior of the moving objects controlled by acceleration to involve more physics for the motion using F equal ma. In the animations, there are a number of moving objects representing traffic vehicles. You can see the brake light come on, and they decelerate and pile up in a realistic fashions. The other cars are waiting for the light to change, and then they will accelerate.
The example involves a traffic signal and sign detected by sensor. Let's have a look. Click Library menus, select the ADAS sensor and moving object, and find three libraries. Select the ADAS sensor for range and tracking, and move to the screen. By the link control, there are three options to attach the sensors. One is steering head, the other is bike frame, and also each of moving object. This dataset selects the bike frame and specifies the XYZ coordinate of the attachment and yaw pitch and roll of the aim angle. Some bikes have a big fairing on the steering head, and in that case, you may attach a sensor on the steering head. You can also specify sensor's range and sensitivity, field of view angle, so on. Next is sign and signal. This is a single moving object screen specifying animation shape and type of sign, which is a speed sign with specifying the speed in meter per second. Also, it specifies the direction which the sign is facing to. The same screen is used to define the traffic signal. Let's watch the animations. As you can see, sensor on the bike detects the red traffic signal and reducing the speed with brake. Then, when the signal turns to green, the bike accelerates and turns at the intersection. Then the sensor detects a speed sign of 55 miles per hour, which is 24.58 meters per second indicated on the plot.
Moving and no-moving objects are not only traffic cars, signs, and signals, but also pedestrians, animals, and bicycles. Let's have a look. This dataset specifies the pedestrians crossing the road by defining initial positions, heading angle of movement, start and stop condition, and speed. Here specify the animation's shape, standing pedestrian shape, and walking pedestrian shape. The other moving object is a bicycle, which will lean in turn. Here the roll angle of the animation shape is specified by an equation involving road curvature. And here is the animation shape for bicycle. The other bicycle is no lean, which is supposed to go straight. Let's watch animations. As you can see, the sensor on the bike detects the stop sign and reducing the speed. Then, two bicycles appear. One is crossing front and detected by the sensor, and the other turns with lean angle. Then a pedestrian walks across the road and she is also detected by the sensor. After passing the pedestrians, the bike turns at the intersection and the sensor detects the bicycle again. You can specify the shape for each object such as cylinder, rectangle, segment, and polygonal. Specifying the shape is very important, especially for occlusions that is explained by this picture. A small object is behind of the other object, and this is completely blocked from the sensor detections. For the circle object, only the left part is detectable. Let's have a look example datasets. This dataset specifies two traffic vehicles. One is a white car and the other is a red motorcycle. This checkbox enables to set the sensor target shape, and you can specify the size and dimensions. And this checkbox enables to show the target shape in animation. The other moving object is an orange dump truck. By the link control specifying one of four different shapes, here select rectangle. And the other dataset is for an object but not moving. This is a wall. The shape is selected to polygonal, and the polygonal coordinate is 300 meters along the road stations. Let's watch the animations. As you can see, the bike and car on the next lane is detected by sensor. Also, the sensor detects the wall but not a dump truck. Now the wall is passed and the sensor detects the truck. Here, the bike on the next lane interrupts the sensor to detect the truck, and the sensor detects again the truck, but soon interrupted by the wall. Another example specifies polygonal shape on the building wall, pillar, and bus. As you can see, the pedestrian behind the building wall is not detected by sensor, then is detected now. The bus also has a polygonal detection boundary.
The next example is using parallel solvers for multiple vehicles. The previous examples are only the one vehicle is full vehicle dynamics and others are objects. But the example I am showing from now involves two full vehicle dynamics models running on the same Simulink model. Let's have a look. Click Tools menu and select Parallel vs Mass Models. This screen links two separate run datasets using the same Simulink model, which can open from the screen. This is a Simulink model with two X-function blocks, one for each run dataset. On this particular Simulink model, the first bike exports XY coordinate of a reference point that is attached on the bike frame. And the second bike imports that coordinate as rider's preview XY coordinates. Now it finished the calculation. Let's have a look at the animation. As you can see, the blue sphere is the reference point which is attached on the first bike. The blue sphere is also the preview point of the rider on the second bike so that the second bike follows the first bike. The parallel solver screen supports up to 20 run datasets. This means that 20 different full vehicle dynamics models on 20 separate run datasets are able to run simultaneously on the same Simulink model.
Parallel solver license is required according to the number of the full vehicles. This is all about the ADAS features in BikeSim. If you go our website video page, ADAS and AV application sections, you can find a number of videos explaining the ADAS features in CarSim that are essentially same as the features in BikeSim.
Thank you for watching this video.